Good morning and welcome to seminar today. Our speaker is Andrea Longobardo. He's a planetary senior scientist from the National Institute of Astrophysics in Rome. He is deeply involved in small body missions such as ESA, Rosetta, ERA, Comet Interceptor, the NASA Moon mission, JAXA IAPS 2, and the CNSA Tianmen-2. He is an expert of planetary surface spectrophotometry and cometary dust, dynamically and physical properties. He is skilled in development of dust sensor for planetary exploration, such as VISTA-ERA, VISTA-RMS, and this Comet Interceptor, and is currently the deputy PI of Diana sensor on board Tianwen-2. So please, Andrea.
Thank you for inviting me to this seminar. Happy to be here for something that is different from the Christmas event that is every year in December. But this year the Christmas event will be in another place, but we don't know which one. Okay, let's come back to science. Disk resolved photometry of small bodies. Disk resolved means that we are looking at images taken acquired from a spacecraft, not from ground. So resolved region of bodies. We are talking about planetary bodies. And photometry. Photometric correction of planetary surface is the removal of influence on reflectance of incident, emission, and phase angles that are here. You can see the definition. The incidence angle is the angle between the solar direction and normal to the surface. Emission angle or emergence angle is the angle between the normal to the surface and the observer, in our case, the spacecraft. And the phase angle is the angle between the two directions, solar incidence and observation. The removal of this trend is a fundamental operation of data reduction, because comparison between different images is meaningful only in the case they are observed at the same observation geometry. Otherwise, we will see differences that could misinterpret, because they are due just to different observation geometry. So we need to lead to the same observation geometry that generally is all the three angles at 0, or incidence and phase at 30 and emission at 0. It depends. And but this is not only a data reduction operation, because the trend of reflectance with the three angles, in particular with phase angles, is related to optical and physical properties of the surface. So by looking at this behavior, we can infer some of these properties, and we can compare between small bodies. We are talking about small bodies, so asteroids and comets. This is just an example. This is a spectra, an observed spectra, and the blue and the red dots are photometrically corrected spectra with two different photometric corrections. So we have to be careful to correction applied, but some slight difference can be present. I will not discuss more about difference of different photometric methods, because the method I'm going to present is in agreement with other methods, so the results are the same. So, but this is just to introduce the issue. The state of the art, the method, the more used method for photometric correction is the ACTI modeling. So is a radiative transfer model which models the reflectance as a function of all the three angles with a series, by means of a series of complicated equations, where 5 optical parameters are retrieved, which is the single scattering albedo, which is the scattering efficiency relative to the total light extinction, strength and width of the opposition surge. The opposition surge is the reflectance rise observed at low phase angle, and the strength is the height of this rise. and width is the width, and the asymmetry factor is the single particle phase function, because we are looking at the phase function of a surface. Phase function is the reflectance as a function of phase angle, and we generally study the average surface behavior, but each particle of the surface has its own phase function, and the asymmetry factor is related to the single particle phase function, and macroscopic roughness, which is the roughness of the surface. This is the commonly used method that has many advantages because it can correct the entire spectrum, but has also some limits. The first one, that is the correspondence between the parameters that I just shown and the corresponding physical quantity, which the optical properties or the physical properties, in the case of roughness, is not always straightforward. So generally, the parameters is not strictly related to the physical parameters. So it could happen that is devoid of physical significance, and there is the risk of degeneracy. We have 5 parameters, so 5 unknowns. If we have a small data set, for example, we are looking at the small regions and not an entire asteroid, but just a small region or a restricted phase angle range, we risk to have degeneracy. These parameters have a large uncertainty and are not well determined. So I developed a new method. Is a semi-empirical approach, which is not better. It's complementary. It gives complementary information, and is based on a statistical analysis of the dataset. Dataset generally camera or spectrometer. And this approach is here presented, and the advantages are, in particular, the analysis of specific regions. In this case, we have not risk of degeneration, because the method is also simple, is faster, and so it allows a fast and efficiency photometric processing method. Then it allows to study photometric behavior of spectral parameters. For example, band depth, spectral slope. In the APT case, you should correct the entire spectra. You should calculate the parameters before the correction, after the correction. So you have these steps to do. In our case, we can take the parameter in the not corrected spectra and correct directly the parameter. So it can be useful for this. For the case. Spectral parameters, I mean, there are many spectral parameters. I just focus here on band depths, so the depth of the absorption band that are observed on a reflectance spectrum, and spectral slope. For spectral slope, I mean the visible spectral slope and the near infrared spectral slope, because our work is focused on these 2 spectral range. And because of the simplicity of the phase function, we can compare very fast and very simple photometric properties of asteroids. We have to introduce just 2 photometric parameters, as we will see later. And it's also possible to assess photometric behavior at varying spatial resolution. So we don't need to merge data taken at different spatial resolution. We can do separate analysis depending on spatial resolution and then compare the results, because photometric properties are also dependent on spatial resolution, especially in disk resolved photometry. And these are the applications done so far. We worked on Vesta with Virgin spectrometer data, on Rutezia and Churyumov-Gerasimenko with Rosetta spectrometer data, on Ceres again with DON spectrometer data, and Ryugu with both spectrometer data on NIRS-3, a spectrometer working in the near infrared range, and ONC camera working in the visible range. So we have also the opportunity to compare different spectral range. The other spectrometers, and VFTs, work in both ranges. I will not go in chronological order, so I will not present a result for each body. I will present the method and main results obtained for each parameter. and for each photometric comparison. So reflectance, comparison between asteroids, role of optical and physical properties in the phase function, band depth, spectral slope, without focusing on each body, but I will recall some result on different bodies depending on the case. Method. This is a photometric empirical method and is a statistical analysis of the entire dataset. I repeat, dataset is a camera dataset on spectrometer data, and the first step is the removal of topography. That means the removal of incidence and emission angle. The equigonal albedo is the reflectance corrected for incidence and emission. There are different dysfunctions. There is a dysfunction available in literature to correct, to model the behavior of reflectance with incidence and emission. These are a few examples: Lambert, Rommel-Siliger, Akimov. There are other more complicated and with parameters, the Akimov parameters version, but just focus on these three. In the first work, we tested all the dysfunction, and the results was that the Akimov dysfunction was the one which allowed to obtain an equigonal albedo independent of emission and incidence angle. We can see the example of Churyumov-Gerasimenko and Liu at least up to 60, 70 degrees. And after that, in the last studies, we did not test all the dysfunction. We just applied the Akimov dysfunction. It worked. Okay, let's go on. The second step is to identify equigonal albedo families. So we have now the equigonal albedo. So we removed the effect of incidence and emission, and we retrieve for each phase angles some values of equigonal albedo, which identify equigonal albedo families. For example, the 10%, the value corresponding to the first 10%, 20%, 30%, 40% of brightest pixel identify a family, and this has been done for each phase angle with phase angle beams of 1 degree. This is an example on Vesta. Each percentage identify an equigonal albedo family. Each equigonal albedo family has a different color. So we have here a 10 equigonal albedo family, and we can see that there are different behavior, for example, from the purple dots and the red dots. We can see that the slope of the phase function is different. This was the case of Vesta, which is an heterogeneous body, but it can happen, and in most of cases this happens, that the equigonal albedo families have the same phase function. So we can, because the body is homogeneous, so we can assume a unique phase function for the entire body. This is the case of Lutetia. This does not mean that phase function is the same everywhere. We can have small regions having a different phase function, but the average behavior can be assumed, can be considered as a unique phase function, not in the case of Beta, where we have macroscopic variation of phase function. In most of cases, we have a small variation at small scale variation, so we can consider one unique phase function. Once we have identified all these equigonal albedo families, or unique equigonal albedo family, we can model that simply by applying a polynomial fit or a linear fit for each equigonal albedo family, or for the unique equigonal albedo family found for the asteroid or for the comet. And this is, for example, the case of Vesta. The equigonal albedo families, we model the behavior of reflectance, but also of other spectral parameters, so band depth and spectral slope and so on. This is the case of Vesta, and we can see that in brighter regions, the phase function is flatter than in dark region. And this and the same is observed on band depth. The band depth increase with phase angles, but the increase is steeper for darker region and flatter for brighter regions. And the explanation is optical, because when albedo increases, the role of multiple scattering is larger, so we have more scattering. Radiation is more scattered at all phase angles, and this results in a flattening of the phase function, because we have radiation at, in a wider range of phase angles. This is the case of Ryugu. In this case, we have a phase angle range in narrower phase angles. See the difference? We have here up to 90 degrees. Here we have observation, available observation up to 40 degrees. So in this case, all phase functions were modeled by a linear fit, so a straight line. And these are example visible and near infrared phase function. Here it is an example of phase function in a small region. This is the impact area. In the IAPS mission, an artificial impact experiment was performed, and here we modeled the phase function of that area, the area object of the impact, before the impact and after the impact. And we have a slight variation. We have a steeper variation that we ascribed, we can see later, to a change of roughness. After the impact, the surface was rougher, and this resulted in a steeper phase function. This is the near infrared and the bandette. I will come back later on the bandette. After that, we can correct. We can apply the correction. We have a polynomial fit which model reflectance as a function of phase angle. We can retrieve all the observation at the same observation geometry. I just show one map as an example, but the result is the same for the other bodies. This is the case of Ceres. We can see here that there are reflectance variation. We can see the variation of the color that is due to a not real reflectance variation, but simply due to the difference observation geometry. And when we apply our photometric correction, we can see that the reflectance range is more restricted, is narrower, because we led to we are removing all the variation due to different observation geometry, and all these continuities observed before correction are removed. We have a more homogeneous map. But however, difference are observed, and in this case, reflectance variation are real reflectance variation. So we are able to study the reflectance partial distribution on the asteroid. To compare different phase function, and here I focus on reflectance behavior as a function of the phase angle. We can, so to compare different phase function of different small bodies, we introduce two spectral parameters: a reflectance at a defined phase angle that could be 20 or 30 degrees. It depends on the phase angle available, the phase angle range available, and the steepness of the phase function that could be calculated on the between 20 or 60 or 50 and 40. Again, it depends on the available observation phase angles. RP and PCS, phase curve steepness. This is the definition in the case we have a range up to 90 degrees. This is the case of Ceres, but also the case of Vesta and Churyumov-Gerasimenko. We retrieve the reflectance at 30 degrees and the slope between 20 and 60 degrees. In the case of Ryugu, we have observation up to 40 degrees phase angle, so our photometric parameters are R15 and PCS calculated between 50 and 40 degrees. And the location of the asteroid or the comet in the scatter plot of reflectance as a function of phase curve function gives important information. In principle, about taxonomy, but also about physical properties. This is the case of all asteroids explored by space missions up to 2020. And we can see that asteroids belonging to the same taxonomic class are grouped together in the scatter plot. These are the achondritic asteroids, Vesta and Steins. They are two different classes, but both achondritic. The S-type asteroids are here. S-type are silicatic asteroids. The C-type asteroids, the carbonaceous one, are both here. So the general trend is a decrease of reflectance as a decrease of phase curve steepness as reflectance increase because of the role of multiple scattering that I said before. There are some exceptions. Lutetia. Lutetia is outside on each circle, is outside of each taxonomic class, and this is a confirmation that it belongs to a different taxonomic class because Lutetia was classified, was also classified as S-type, and this result confirms that is a different taxonomic class, is an XK type. Another exceptions, the Vesta dark regions, because the dark regions of Vesta are mixtures of achondrites, in particular HED, and a mixture of carbonaceous chondrite that is the main component of C-type asteroids. So a mixture between the two end members is quite in the middle between them. So is something expected, but it is confirmed by this result. But there is not only influence of taxonomy and the composition, but also a influence of physical properties, in particular roughness. This is the case of the Occator region of Ceres. Occator is a peculiar region of Ceres, and it shows a phase curve slope steeper than expected from its albedo. We should expect that Occator is here, but it's there, is higher. And this has been ascribed to the larger roughness of Occator, because when roughness increases, radiation is more extincted by the roughness itself of the terrains, and this results in a steeper phase function. And this was observed for Occator, but was more evident, still more evident for comets. Comets, these are old comets explored by space missions. All comets have similar albedo, so we should expect a similar phase function steepness, but we have a variation, and this variation has been ascribed to roughness. Comets have very different roughness because each perihelion passage smoothens the surface because of the activity, because of the ice sublimation, and this ice sublimation makes the surface smoother. A comet that had more perihelion passages is smoother than a comet that had less perihelion passages. So a more primitive comet with few perihelion passages is more similar to asteroids, Virtue. And when the comet is more and more as a larger and larger evolution, its phase function becomes flatter. And so we are able to identify photometry as an indicator of comet roughness and a comet evolution state. And this is not observed only for comet as a whole, but also for single regions of the same comets. These are the phase functions steepness obtained for 4 regions of the Churyumov-Gerasimenko comet, and we can see that the 2 rougher regions show a phase function larger than the 2 smooth regions. And this result is also confirmed by an independent dataset of the camera, of the OSIRIS camera. Another parameter which affects the phase function is the spatial resolution, because I give the conclusion before the conclusion and after the results, the conclusion is that the comparison is meaningful only if spatial resolution is similar. Which means similar means that we have a variation of phase function shape when spatial resolution is smaller or larger than 100 meters, more or less. We can see 100 meters is the threshold above which or under which the phase function shapes changes. This is the case, for example, for IDA. In the case of a bright surface, so bright means brighter, the albedo larger than 0.05, albedo at 30 degrees. IDA shows a phase function steeper than the other S-type asteroids belonging to the same taxonomic class. But IDA is observed at a better spatial resolution. This is observed because when we increase spatial resolution, we highlight the heterogeneities of the terrains. And this led to a larger variation of reflectance even between different phase angles. So when spatial resolution is worse, we have a sort of average. And for this reason, the phase function tends to be more homogeneous. But when we increase spatial resolution, all the heterogeneities are highlighted. And this results in a phase function steepness. The reverse behavior is observed for dark surface. We were surprised when we saw that Ryugu has a phase function flatter than other C-type asteroids. But Ryugu is observed at better spatial resolution, a few meters of spatial resolution. And in this case, we have the reverse behavior because when in dark surface, phase function is affected by shadowing. So we have dark features on the surface which produce the effect of shadowing and reduce the reflectance. When we increase the spatial resolution, these shadows are in some way removed, and this results in a phase function, more homogeneous phase function, so is a flatter phase function. When Ryugu is observed at a worse spatial resolution, and we verified that, worse than 100 meters, it shows a phase function steepness comparable to other C-type asteroids. So everything is in agreement. Now let's see the behavior of other spectral parameters. Depth of absorption band, the general behavior independently of the band carrier. So we are here seeing band due to different carrier. 1 micron band is due to pyroxene, 2.7 micron band on series is due to phyllosilicates, so is a different carrier, but the behavior is generally the same. A band deepening with phase angle increase, and this is due to the fact that when we increase phase angle, we increase absorption because the optical path is larger, and so band is deeper. But again, we have exceptions. If we have a very, very bright carrier, we increase multiple scattering. This is the case of carbonates on series. They are very bright carrier. And in this case, multiple scattering removes any influence on phase angle. We do not have a trend. And again, the same decreasing, increasing trend is removed when we have a dark surface. This is the case of Ryugu. The 2.7 and 2 micron band depths decrease with phase angle. Which is the interpretation? When we darken the surface, we have more opaque materials, and these materials suppress the reflectance, but suppress also any trend of reflectance. And in fact, we have the case of Churyumov-Gerasimenko, which has a smaller albedo than series. In this case, the reflectance behavior with phase is the band depth behavior with phase is removed, and we have no trend, a constant behavior of band depth with phase angle. When we further darken the surface, the reflectance at at high phase angles are suppressed before than the reflectance at not the reflectance, sorry, band depth at a high phase angle are suppressed before than band depths at higher phase angles, at lower phase angles. So this generates a decreasing trend as observed in the case of Hugo and confirmed also on meteorite. Marchinson, which is darker than Hugo, also shows a decreasing trend of band depth as a function of phase angles. Let's move on phase reddening. Phase reddening is a well-known phenomenon in spectrophotometry and refers to the spectral slope behavior with phase angle. Spectral slope, both visible spectral slope and near-infrared spectral slope, which are red, so steeper, when phase angle increases. This is related to the interaction of radiation with single particles. So radiation with the roughness of single particles and generates this trend, this reddening trend. And this is important to understand what happens between darker surface and the brighter surface. Phase reddening, and for phase reddening, I mean this slope, so the slope of this straight line is generally greater in the visible spectral infrared with respect to the near infrared. And for example, in the case of Ceres and 67P is 3 times the visible phase reddening with respect to the infrared space reddening. But in the case of Ryugu, we have comparable phase reddening, and we try to understand why this is observed. And we have 2 possible explanations: an optical explanation and a physical explanation. The optical explanation is the absence of multiple scattering, so we have a constant phase function from visible to infrared. Basically, the reflectance does not change between the 2 spectral ranges, and also the phase reddening is the same because the reflectance is the same. This is a possible explanation, but is not fully convincing because also in the case of other asteroids which has a constant reflectance, this variation between visible and infrared phase reddening has been observed. For example, in the case of Ceres, there is not a strong variation of reflectance between visible and near infrared, but the phase reddening varies 3 times. So we talked about physical properties, because since phase reddening is due to interaction of radiation with particle roughness, visible and near infrared radiation have a different wavelength, so it scatters differently from the particle roughness. But if we have a very smooth particle, the interaction is the same because there is smaller roughness, and this could be the case of Hugo. Or another possible explanation is there are variations with submicron roughness, but they are masked, they are both extinct from the low albedo. I think that the first explanation is more reliable for 2 reasons. The first one is that Bennu, it is another asteroid that has been explored by space mission, as a reflectance similar to Ryugu, but this is not observed. So also in the case of Ryugu, the visible phase reddening is larger than the infrared one. So if this explanation was correct, we should observe the same behavior on Ryugu and Bennu. Otherwise, since from both asteroids, Ryugu and Bennu, samples have been brought back because we are talking about sample return missions, which taken some samples of the two asteroids and brought back to the Earth. And from the analysis of the returned samples, it has been observed that Ryugu particles are smoother than Bennu particles. So I didn't know when I wrote the paper that that this could happen, but it has been it has been highlighted from following papers. So the most reliable explanation is the smoothness of the particle of Ryugu. So, conclusions. The application of the photometrical empirical method on small bodies give some different outcomes. The first one is an easy comparison between spectrophotometric properties of asteroids, and these are related to the state of the asteroids, to the evolution scenario, to the local processes, because we have a small scale variation, to surface modification. So we are also able to identify regions with distinctive photometric properties that could identify, could evidence physical variation, and physical variation could be due to evolution process, different evolution process. So we can, in some way, to reconstruct the story of that region and of the asteroid or the comet as a group. Analysis of spatial resolution is related to surface heterogeneities in the case we have bright asteroids, and shadowing in the case we have dark asteroids. The study of band-depth photometric behavior is strictly linked to optical properties on the surface, and by studying phase reddening, we can characterize regolith particles from both an optical and physical point of view. That's all. Thank you.
Okay. Questions? So for people online, you can write the questions in the chat, or you can raise your hand. So question? Jim?
Just an ignorant question. Was a graph where you had all the light bodies and things like Vespa and the types of asteroids. Was there the E asteroid was grouped close to the Vespa trend?
E asteroids.
Is that correct?
Yes, Times. Yes, Times was grouped, no, is alone because it's the only E-type asteroid explored, but was close to Vesta, which is a B-type asteroid, and both are achondritic asteroids. So that's why I grouped together, but they are two different classes, but both achondritic and both grouped together.
So it's the fact that they're grouped closely on this graph is because they're both chondritic?
Yes, yes. We have achondritic and chondritic. We have, I didn't mention. But we have also a clear separation between achondrites and chondrites.
Okay.
We have taxonomic class, but also achondrites and chondrites.
So also, if you group the chondrites and the non-chondrites together, there's a trend. They both have altogether kind of I understand there's.
Yes, because the main factor that causes this trend is the albedo. So the main parameters is the albedo, and when albedo is similar, we can see variation due to other properties, but the main factor is the albedo.
Other questions?
People online. Okay. So I have a couple of questions.
Yeah.
Andrea, at the beginning of your presentation, you show you summarize the different photometric correction methods.
Mm-hmm.
So did you apply all these methods to the body you show to compare how this method work?
No, I
Which
didn't
is the
apply.
better one to use?
No, I just applied the photometric empirical method, but for each mission there is someone which applied the IAPS method, so I had the opportunity to compare. So for Dawn, there was the correction by Mauro Ciarniello,
Okay.
and for Hayabusa 2 by Eri Tatsumi, they both applied the IAPS method, and so the two methods gives the same results in terms of phase function.
Okay, but so you use just your empirical methods and the IAPS. So you didn't consider also the other.
When available, in the case of Vesta, there was another method, the Shkuratov, applied by Stefan Schröder. When available, I compare with everything. But generally, the only available is the active one.
Yeah, for the other body, no.
No.
Just for that. And the other one is regarding the plot you showed about the carbonates of series. So the one with no trend. In this case, is there a way to apply phase correction or not?
There is no trend, so there is no need of phase correction. So you can take the band depth and just work. What is important to say about the series? Okay, there is a question. The 3.4 micron band, this carbonate is only one of the carrier of the 3.4 micron because it is a combination of ammoniated phyllosilicates and carbonates. And on the Okator regions, there is no trend, but on other regions, there is a trend, a decreasing trend. So in this case, there is a larger abundance of carbonates, and in the other case, there is a smaller abundance of carbonates, so we are able to see the trend of this band. So we are also able to infer this kind of information.
This is just a little bright material, so it's bright and
bright, and in this case, because bright is due to abundance of carbonates, and on the Okator there is a larger abundance of carbonates.
Okay. So other questions?
Yes.
Okay.
How did you determine the equigonal albedo families for Vesta? And once I applied the Akimov this function here. Each value for each phase angles, we have 9 values. One corresponds to 10% of brightest pixel. The second, 20% of brightest pixel, 30%, 40%. So each value is related to a percentage of bright pixels. The same percentage for the entire phase angle range identifies an equigonal albedo families, and here are highlighted by different colors.
Thank you.
Okay.
Thank you.
Other question? No. Okay.
Thank you very much. Just a few. But for example, the difference in the phase value, you show that it's really related to part. Yeah. Can you also do, for example, the spatial resolution data?
Spatial resolution is quite the same, is similar for the two missions. There is no as.
So there's no influence from the.
No, I don't think that there is a. They are two very similar missions, so.
Okay. Other additional questions for Andrea? Or people online? Okay. If there are no other questions, thanks again.
Thank you.